Hi, this is an example problem from Chapter 9 on equilibrium. Pause for a moment and read the problem. So you can see in the picture that's been drawn there, we've got a diving board and we've got a woman that's on it and she's standing still. So everything in that picture is motionless. The velocity, translational or linear, the angular velocity, they're both zero, and this is therefore a case of static equilibrium. That means everything is balanced. All the torques are balanced, all the forces are balanced, and there's zero acceleration. The conditions for equilibrium, just to remind you, are which I just mentioned. The net force in the x and y directions are zero, so the forces are balanced in both directions. And finally, the torque is balanced about any axis of rotation. If you add up the net torque, you get zero. So we're going to use these conditions to solve this problem. Now, to do a problem like this, it's kind of like doing Newton's second law in a sense. In this case, everything equals zero because there's no acceleration. And before we used to draw free body diagrams. In this case, we need to actually draw the full picture because when we calculate torque, we need to know the radius from the axis of rotation to the point at which the force is located. So we need to accurately draw the position where all the forces act. In this case, we're going to focus on the diving board. That's the object that's in static equilibrium. And the other things touching it, they are producing forces. So let's go through and go through and identify the forces that are acting on the diving board. So I'm going to go ahead and do the contact forces first. We've got a normal force here that pushes straight up on the board. Let me call this one F sub n. And we've also got the bolt force. Now we know this end of the board would pop up if the bolt wasn't pushing it down. So in fact, the bolt force pushes it downwards here. I don't know how long these forces are, but let me go ahead and just write them down here. I guess the fulcrum force, the normal force here, is actually what we're calling fulcrum force. So let me change that. And finally, the woman is pushing down there on the object, on the diving board, due to a direct push force, which is equal to her own weight. So we've got here the force of the woman pushing down on the board. Now we've got all the contact forces, nothing else touching the board. However, we still have the gravitational force that we need to consider. And so for the gravitational force, it has to act at the center of mass of the object. Now this is a symmetric diving board, and so the center of mass can be right in the dead center there. I'm going to call this, well, let me go just draw it like this, little point right here. I'm going to call it center of mass for the board. And so the weight of the board, we can consider it to be all concentrated at the center of mass there. That's the gravitational force on the board, and we want to use that position when we calculate torques. All right, we're trying to calculate the magnitudes of two of these forces, all right? So we already know what the woman's weight is, so we can figure that force out. We know what the mass of the board is. We can figure out the gravitational force of its own weight. And the things that we don't know, we're trying to figure out what is the magnitude of FB here, right? What is the magnitude of the fulcrum force? Two things. Well, we're going to go ahead and do this by using the equations for equilibrium. And I'm going to start with the torque equation. As we'll see, this is a special equation. It's the best one to use out of these three because it allows us to choose the position, which is the axis of rotation. So for example, let's say I want to try to calculate what FB is. So I'm going to focus on this one first. I don't know anything about the fulcrum force, so I'm going to go ahead and put my axis of rotation right there. So here is the axis of rotation. Now you might wonder, why did I choose it to be there? In fact, if something is in equilibrium, static equilibrium, I can choose this axis of rotation to be anywhere because any axis is going to give you a net torque of zero because it's not rotating about any particular point on the board. So we're free to choose that, and that's a huge advantage here, as we'll see in a second. So let's go ahead and calculate the torque. So we're going to go ahead and use the net torque equation here, right? So the sum of the torques equals zero. And in this case, we've got 4 different torques, right? I'm going to write them like this. We've got the torque due to the bolt, plus we've got the torque due to the fulcrum, plus we've got the torque due to the board's own weight, the gravitational force on it, plus we've got the torque of the woman pushing down on the board. And they all need to sum to 0 because it's at equilibrium. So we need to go ahead and calculate individually each one of these torques. And we can go ahead and write down for the bolt first. Remember the general equation for torque, plus or minus the parallel component, sorry, I just said the wrong thing, the perpendicular component of that force to the radius, okay? I think I usually write the radius first, doesn't matter. So in this case, we're going to always measure the distance from the axis of rotation straight out to the point where the force is applied. So that's the radius for the bolt there. And we can go ahead and write this down. Now I need to ask, for the force that is the bolt force, is that going to produce a torque that causes the, if you look at that by itself, will this force here, will it make the diving board go rotate clockwise or counterclockwise? Well, it's downwards from the axis of rotation. This thing here is naturally going to produce a counterclockwise motion. Therefore, it's going to be positive. And so we can write down a plus. I don't know what the magnitude is of FB, but notice that it's all perpendicular to the radius. So it's going to be the full magnitude FB, whatever that is, times the radius RB. And we know what that is. It's 1.4 meters. So that's what we have so far. Let's go on to the next torque. Next one is force of the fulcrum. Here we're going to see why our choice of axis of rotation was good, right? Plus or minus, I'm going to write the radius first here. And we're going to say, so R for the fulcrum times the perpendicular component of the fulcrum's force. This is 0. Do you know why? Because the radius is 0. Look at the radius right there. It is got 0 radius because the force is applied at the axis of rotation. And so we just automatically wipe that torque out due to the fulcrum by clever choice of axis rotation. Let's go on to the next one. Torque due to the object's own weight, or the gravitational force that acts on it. Again, same thing, plus or minus the radius for gravity times the perpendicular component of that force. And if we look at it again, let's draw that radius here. So it's going to be, here's the axis of rotation. There is the fulcrum, right? And so this right here, that is the radius for that gravitational weight force. We're going to go ahead and figure that out, right? So the whole board is 3.9 meters, right? And so half of that board, if we go, let's say, from here to here, 3.9 divided by 2 is going to give us a value of 1.95 meters, right? And so this distance here that we need to figure out, right? That's going to be 1.95 minus 1.4. And that's going to end up giving us 0.55 meters, okay? So now we know the radius for the board's gravitational force, and now we want to figure out what is the plus or minus sign. Well, look at this force here, and here's the axis of rotation. This force is going to cause it to go clockwise. So that's going to be negative, right? So we're going to choose the negative sign here, just like we chose earlier the positive sign. So we got a negative. The radius is 0.55 meters, as we said. And the magnitude Fg, well, look at it's all perpendicular. Again, if we look at the radius and the direction, perpendicular already, so it's the full magnitude. Remember that Fg, the magnitude of Fg, that's just equal to the mg, the mass times gravity. So the mass here of the diving board, 50 kilograms, and 9.8 meters per second squared for g. So we've got a value there. Finally, For the torque due to the woman standing at the edge of the board. Same thing, plus or minus the radius to the woman times the perpendicular component of the woman's force. Let's draw the radius for the woman. Start at the axis of rotation and go all the way out to where her force is applied, and we can see that that's 1.95 plus 0.55, which is going to give us 2.5 meters. And again, her force is already perpendicular to the radius, so the whole magnitude, whatever Fw is, we're going to put that into the equation. It's all perpendicular. And in fact, we're told that she has a weight of 530 newtons, so that's how hard she's pressing down on the board. So we can go ahead and write that down. Oh, before we got to check, we got to see, is she going to make that board, her force alone, going to rotate clockwise or counterclockwise? We can see that hers, for that rotation axis, it's going to be clockwise. So that's going to be negative. So we've got a negative 2.5 meters multiplied by 530 newtons. And let's go ahead and just simplify some of these numbers here. So the first torque we can write as a positive 1.4 meters times FB. Next one 0. The next one we can write that as a negative 269.5. Let me get a little more space here. That's a negative 269.5 newtons times meter. And for the next one we have here, negative 1,325 newtons times meter. Now what are we going to do? Well, we're going to go ahead and do what the equation tells us to do right over here. We're going to go ahead and add up all those torques and set them equal to 0. All right, so for the bolt, we've got a 1.4 meters times FB. For the fulcrum, 0, plus the torque of the board's own gravitational force, going to be a negative 269.5 newton times meters. And finally, for the woman's torque, it's a negative 1,325 newtons times meters. And add them all up and equal to 0 because it's in equilibrium. Finally, we're going to solve for FB, right? So that gives us a 1.4 meter times FB. We're going to add both those other torques to the other side, and when we do that, it comes out a positive 1,594.5 newtons times meters. And finally, we're going to just divide by 1.4 meters on both sides of the equation. We'll cancel out our meters and we'll be left with the newtons of force applied by the bolt. And so plugging that into the calculator, this is what we get. About 1,139 newtons of force. And of course that's positive since that FB is a magnitude. Now we want to go ahead and we just figured out the force by the bolt. Now I want to figure out the force by the fulcrum. We could go ahead and redo the same process that we just did. And this time, if we want, we could choose to put our axis of rotation right here if we want. Ignore this one. And then we wipe out the bolt and we could do the fulcrum just like we did before. I'm not going to do that though. I'm going to go do it in a slightly different way. I'm going to go ahead and use the net force in the y direction equation, right? So equilibrium, that means that when we add up all the forces in the y direction, they sum to 0. Why did I choose the y direction? Well, look at all the forces. They're all vertical up and down, so they're all in the y direction. And all their magnitudes are either positive or negative in the y direction, right? So I'm going to look at these 4 and let me go ahead and put them in there in terms of magnitude, starting with the bolt. Bolt, it's going to be a negative magnitude of the bolt, right? because it's down. The next one, the fulcrum, it's going to be a positive, whatever the magnitude of that is. It's all up. For the FG, it's all going to be down, so that's negative. And same for FW. It's all the magnitude going to be down. Add them all up, they must balance, and you get 0, right? So let's go ahead and do a little bit of algebra and just solve for the fulcrum here, right? So force of the fulcrum, in that case, I'm going to have to add FB to that side, add FG to that side, and I'm going to have to add FW. So there we go. And finally, let's put in some values here. Force of the bolt, that is what we just figured out, 1,139 newtons. The weight of the board, M times G, 50 kilograms times 9.8 meters per second squared. The weight of the woman, 530 newtons, was given to us directly. And now we need to go ahead and just add those all up. And when we put that in the calculator, this is what we get. 2,159 newtons. That's the force of the fulcrum there. And so that wraps us up for this example problem of static equilibrium.